Hello, everyone. I'm glad to see that people made it. I hope I didn't get people too confused with my wrong time zone conversions. Today we have Torgeir Aambø from NTNU, Trondheim, who is going to speak about deforming chromatic homotopy theory. Thank you.
So yeah, thank you for the introduction. What has become like a tradition in this seminar is that whenever we don't have any speakers, we just decide to speak ourselves, which is the fun part of being an organizer. And this is also the case this time. So I have the pleasure of saying some things about stuff I'm currently thinking about, which is deformations of chromatic homotopy theory. So I'm going to tell you a little bit about which kind of deformations already exist, what deformations are, and which kinds of both problems and interactions which arise when trying to do this in a nice way. Okay, so roughly the goal is to see like a quick introduction to chromatic homotopy theory, because we need to be on the same page about what we're discussing. And then a quick introduction to the deformation theory of stable infinity categories. This will also be very brief and not too precise, because we really want to dig into the different things in the two last sections, which is like the deformations that already exist about like deforming EN local spectra. And on the last part of the talk, we'll discuss potential deformations for KN local spectra. So EN local spectra deform very nicely. They're like a very nice category. Some problems will arise, and there's like a lot of issues with doing anything KN locally, because KN localization is not as good of a functor as EN localization, but we'll get to that. Okay, so first some introduction to chromatic homotopy theory. There's a lot of different ways to introduce chromatic homotopy theory. And basically, which way you use to introduce them is like how you're gonna think about the theory. So you can use it or go about it, for example, via formal group laws. I'm gonna like not do these ones. I'm just gonna. This will show up roughly later, but I won't say much about them. But there's a connection between stable homotopy theory and formal groups, which is where like chromatic phenomena arise in stable homotopy theory, because formal groups are stratified by an integer called its height, and you can kind of use this to stratify stable homotopy theory with a bunch of different layers, giving you chromatic homotopy theory. There's also related but somewhat different perspective via TT geometry. So you can design the Balmer spectrum of stable homotopy theory and then study which kind of functors do which kind of things on this Balmer spectrum. And this gives rise also to chromatic homotopy theory. There's several other interpretations as well, but the one we're going to focus on now is by using certain minimal localizing subcategories. So first off, what is a localizing subcategory? So a subcategory, D in some. I'm going to be a bit like not too precise about which categories we use, but mostly this will be like symmetric, monoidal, stable, presentable infinity categories. Usually also compactly generated with a set of compact generators that are also dualizable. So these are like very, very nice, stable, symmetric, monoidal infinity categories. So if you have your like favorite example in your head, like, I don't know, for me it's like spectra or something, and these are examples. And usually the things we work with like in stable homotopy theory are usually of these kinds of categories. So a subcategory D of C is localizing localizing subcategory if it is a stable closed under the three common limits. So it's just some very nice way to take a kind of smaller version of the same category or same category with some kind of information inherited. Okay, so we can take a set of compact objects. So if I have a set K of compact objects in C, then I can generate a localizing subcategory. We're just taking, which is denoted like loc, or no, I'm not doing tensors, I guess, which is just the smallest localizing subcategory containing the compact object K. We can also make this into asymmetric monoidal category by also assuming that if we assume that that C times D is in D for all C in C. So this is like having like a sort of ideal property for subcategories or elements in the subcategory. Then we call D a localizing ideal. And the localizing ideals, they inherit symmetric monoidal structures from the category C. So if we have a localizing subcategory, then we also have a symmetric monoidal structure on this category. Okay, so I'm just gonna remove this. Okay, so the question, or chromatic homotopy theory, kind of arises out of the question of what is the minimal localizing subcategories of the category of spectra. So a localizing we say a localizing subcategory is minimal if it has no localizing subcategories itself. If so, call it again D, if all okay, so it just means that the localizing ideal or localizing subcategory itself doesn't have any more localizing subcategories contained in it. It's kind of the last stop of doing localizations or taking localizing subcategories. Okay, so the question is, what are the minimal localizing spectra? So this is a perfectly fine question you can ask. It does currently, as of today, not have an answer. It's terribly difficult to figure out because, yeah, there's a lot of things happening in spectra. It's a very complicated and rich category. But we have some sets of minimal localizing subcategories. So chromatic homotopy theory is about these kind of categories. So examples are, you probably all heard about the K-n local spectra, which is what we're going to focus on today, but also, for example, T-n local spectra. There are also minimal localizing subcategories. And of course, just recently, we have learned that these two are not the same type of category. So we know that there's different kinds of minimal localizing subcategories. There are kind of different species of them. And there could be others as well. We have no idea. Like there's some proofs that try to relate K-n local spectra and T-n local spectra. And for any like one for those in the know, if you have a one semi-additive ring R, then SPR is also a minimal localizing subcategory, and it sits like between these guys. So so potentially, if there exists any other semi-additive rings, then we would have more types of minimal localizing subcategories. But we currently don't know whether these exist or not. So we're just going to focus on the one that we can actually understand, which are these guys. We can understand some things about T and local spectra as well, but they're kind of more complicated, at least from the perspective that we need for the talk.
Hey, can I ask a question?
Yes, of course.
How do these inclusions not contradict minimality?
Good question.
So as it is said in chat, they're localizing, but only one is minimal, right? They're all localizing subcategories, with the KN local spectra being the minimal one.
Yes.
But yeah.
There's something I'm missing as well. I'm gonna think about it, but in a certain sense, these TN local ones are also minimal. But it maybe how I've phrased it, they're not minimal in the kind of correct thing, because the KN local ones are certainly like the minimal ones if you think about localizing subcategories in terms of thick subcategories, because these are slightly easier to do. And then we have a very nice like thick subcategory theorem that tells us that KN local spectra are all the thick ones if you only care about finite spectra. But in the world of non-finite things, then things get horribly much more complicated. Yeah, I'll try to have it in the back of my head if I can cook up a way to see this. But yeah, you're correct. This like maybe it doesn't make sense to say that they're minimal and that this stupid thing works. So let's just ignore these for now.
Thank you.
But yeah, good question actually, because that I agree that doesn't make sense. Okay, so we have these KN local categories. They're very important in understanding the structure of stable homotopy theory. Precisely because they're like minimal pieces of the stable homotopy category, we can build everything we want out of these guys. At least we can build every finite spectrum out of KN local ones. So in a sense, then as stated in the weird abstract I made for this talk, then these are like the subatomic particles of stable homotopy theory, like the smallest possible thing you can use to create all the different other spectra. Okay, so which kind of things can we create? So KN here is for I haven't actually said that yet. It's called the Morava K theory. And there's also a prime P hidden in the notation that I won't say much about. The prime won't be that important for this talk, but for every prime we have a Morava K theory at height n at that prime. Okay. So n is just this height integer that I was mentioning earlier that is like forms the stratification of formal groups. So if we take, I'm going to define, I guess, SPN to be the category of spectra localized at K0, wedge, blah, 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 up to Kn. So I'm going to take not only a single height, which is like the SPKN, but I'm going to take all the heights up to n. So I'm going to take height 0, height 1, height 2, blah, 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 up to all the way up to height n. And this is called the height n category or something like this. There's also another spectrum that we can use to produce this category, which is much nicer than just wedging together a bunch of Moravec theories. And it turns out that there's like a nice E infinity spectrum that we can do this with. So we can also localize at some E infinity spectrum En, which is like Moravec theory or Lubin-Tate theory, or it has a bunch of different names depending on precisely what you mean with writing En. There's also different kinds of non-E infinity versions, like E1 versions called Johnson-Wilson theory and completed Johnson-Wilson theory, and a bunch of different things. For the purposes of this talk, it doesn't really matter so much. But there is some spectrum that you can use to produce also this phenomenon. Okay, so how are these all related? So the way I view chromatic homotopy theory is like through the lens of local duality. So and this is kind of a categorified version of the chromatic fracture square. So from if I have some En local spectrum, some spectrum in this category, so I have some X, then I have a fracture square relating this En local spectrum to the Kn local one and the En minus 1 local one. And the statement is that this is a pullback square, homotopy pullback square. So you can take this information that's kind of ingrained in this diagram. This is called a chromatic fracture square. And it works for like any En local spectrum. And I can categorify this into a relationship between these different categories. So I have my category SPN, and I have my other category SPN minus 1. So now I have this guy, this was an En local spectrum, and I have this guy, which is En minus 1 local. And I have, how do adjoints work when you write them horizontally? The left adjoint is to the left, right? Yes, that makes sense. So this is just Ln minus 1 localization, and this is just the inclusion. And this has for every localization, if I take some Ln local spectrum and I take the fiber, now I'm running out of space on this guy. Then take the fiber here. This is called like the monochromatization of X. And this is also a category called the monochromatic category. It includes and has a right adjoint. And if we take it's called the orthogonal category to this guy inside of this, then we get the Kn local category. And we have a left. Now the left one is on top. That should be also good. And these ones are equivalent. So this is called local duality for chromatic homotopy theory. And it's basically like a categorification of exactly this fracture square diagram. So anytime you have a local duality, this is a much more general phenomena. You can have local duality in a bunch of different other things than chromatic homotopy theory, and these are always like categorified versions of certain fracture squares. So what will be like important for us later is that if we have some category that is related to this middle guy, SPN, or EN local spectra, then if we are able to produce some sort of local duality diagram like this, then we also have some sort of way to get information about KN local things. So we'll shortly try to like cook up some deformations of EN local spectra, and doing some similar type of thing like this should allow us to construct some version of deformation theory for KN local spectra. Because as I'll also say, like doing KN local deformation theory like just out of the box, just trying to do it for KN is quite difficult. Okay, so let's turn our heads to deformation theory. I've already like spent too much time maybe on chromatic ones, but chromatic homotopy theory is fun, so it's not too bad. Okay, so I'll be a bit quicker than on the deformation theory. So deformation theory is it's not just one kind of the deformation theory of stable infinity categories. There's a bunch of different ways of doing this. So I'm going to be very vague about what I mean with deformation theory. I'm going to say like roughly some ingredients that we should have, but these are not formal requirements, and they're not always there in the theory. So the thing we're going to focus on is sometimes called like, I guess I need to look at how before deformation theory. So if I have some symmetric monoidal stable infinity category, very nice. It's perhaps compactly generated, whatever. There's some nice or even more stronger statement. Okay, and we also require with I want the category and its unit, the unit in the symmetric monoidal structure, to have an endomorphism of degree -1. Okay, so this is like things that are required at least for the tau deformation theory. And by having this information, you can produce two categories. So I can produce one category called the generic fiber. And I can produce another category called the special fiber. And these are roughly created by inverting tau and killing tau. So I'm gonna not be very precise here, but there's a way to invert tau, and there's a way to kill tau. These are now two different symmetric monoidal stable infinity categories that have properties that kind of relate them to the big category D. And we should think about this category D as kind of being a deformation between these two categories. So in some sense, I start off with I can think about inverting tau is kind of like saying that tau is equal to 1, right? So I have my category D, which has an endomorphism of the unit, and putting tau equal to 1 gives me another category, tau inverse, and saying tau is 0 gives me another category. And this category D kind of lives in between these two categories and deforms between them. So we say this is not a very precise setup, but it doesn't matter that much. We'll be a little bit more precise in the examples. And the way, or the reason I'm not like very formal is because the different examples require different kinds of definitions for what a deformation should be. They all have roughly the structure. So this is like a meta definition in some way. But being very formal about what this should all mean, one needs to use some sort of more specific situations. For example, you can use filtered spectra or filtered objects. And then this will be like you can do this very formally, or you can set it up using other machinery, using sheaves, for example. But yeah, this is like a very brief meta definition of what a deformation between two stable integers should be. So we say D is like the tau deformation between the category D tau inverse and D tau equals 0. That's kind of the idea we should have in our heads. Okay, so let's try to construct some examples. And the examples we are interested in are, of course, deforming chromatic homotopy theory, the EN local case in this example. So we want some sort of diagram such that we have EN local spectra on one side, and we have some sort of deformation D, so that if we invert tau, then we get EN local spectra. And we should have some other thing on this side, which I haven't been too precise saying what is. But this should be the derived category of a certain abelian category. Why is this the case? Well, we're interested in studying kind of ways to deform between spectral stuff and homotopy stuff and algebraic stuff. So this algebraic stuff is the closest algebraic thing we have to chromatic homotopy theory, and to be more precise maybe than this D E star E, this is the derived category of comodules over E star E, which is like it's a Hopf algebroid. It's the term to use, but this is just some Grothendieck abelian category. Very nice category, and you can form its derived category because it's so nice. And this guy is just a derived category of that one. Okay, so this is the kind of thing we want. This is like saying tau equal to 0. Okay, so what are some examples? There, as I said in the beginning, there's a bunch of different examples of these deformations already existing. So maybe the most famous one is Piotr Pstrągowski's synthetic spectra. And in this particular situation, we're using the hypercomplete synthetic spectra. So what are these guys? So the category of hypercomplete synthetic spectra based on En, is the category of additive sheaves of, or spherical sheaves of spectra on some nice site that I'm going to call SPFP. And these are finite spectra such that its E homology is finitely generated and projective as an E module. So these are SPFP, are so if I take some spectrum, then X is in finite spectra, and its E star homology is finitely generated and projective. And being a finitely projective,
repeat, sorry, what the sigma means here?
Yeah, so this sigma guy means means that what is it? You send the co-products to products or products to co-products.
Preserve finite products.
Yes. Yes. Yeah, so being finitely generated and projective as an E-star module is the same as being dualizable in the category of comodules. So if you can also think about this SPFP as being like those finite spectra such that its E-star homology is like a dualizable comodule. This is equivalent ways of thinking about this. And here I need to use hypercomplete sheaves instead of just all sheaves. Otherwise, we will not deform the correct category. Okay, so these guys have like the proper, there's the degree -1 endomorphism of the unit called tau, which is like imported basically from motivic homotopy theory, and all of these like analogies comes from motivic homotopy theory. But we have like a correct deformation thing between EM local spectra and this derived category of E star E. There's also I don't like particularly hypercomplete synthetic spectra. The synthetic spectra in themselves are kind of nice. They're like the global version, but if you want to do things EM locally, then you should kind of, it feels ad hoc to me to just reduce to like hypercomplete synthetic things. So you can instead use an internal model, which I've started denoting, for example, like LE sin E or something. I haven't found a very good notation for this guy yet, but there's several choices, all with some good properties and some bad properties, as all notational problems have. But this is like, again, all sheaves of spectra, but instead of using just the site of finitely E star projective spectra, then you take only the ones that are already EN local. So in this way, you don't have to worry about things being hypercomplete or not. Automatically, all sheaves in this category are hypercomplete, so you don't have to worry about like ad hoc afterwards hypercompleting stuff. And this is just, in my opinion, a much cleaner way of phrasing these things. So again, this gives us the same picture. I'm just going to write it. So this guy is equivalent to hypercomplete synthetic spectra. And we have several other models as well. So just let me quickly just mention a couple, because they will maybe show up. So this is synthetic spectra, and then we have so in joint work, Piotr and Irakli Patchkoria, they made like a generalization or a slightly different version of synthetic spectra that works not only for spectra, but that works for like more general stable infinity categories. And these are called like perfect derived categories, or perfect sheaves, or whatever perfect derived category is usually the way to go. And these are I'm going to use this notation, I guess. And these are also like certain subcategories of sheaves. So the ones important for us, this will be E star homology and spectra. These are described in Piotr and Irakli's big long paper proving Franke's algebraicity theorem. A very cool paper, but it's like 100 pages of technical details and remarks. But still a very fun read, so I would recommend it for everyone. Yeah, this is I'm not gonna have the time to properly define a bunch of these guys, but okay, I'm gonna say vaguely what these are. So you take, this is like a full subcategory of all pre-sheaves. these spherical presheaves on spectra, and I take only certain ones that are generated by the representables that are also closed under finite colimits. And then I sheafify with respect to a very specific topology, which is the topology generated by the E epimorphisms. So any map that E star F is then an epimorphism, and I'm going to call that like a cover in my pre-topology, and I'm going to sheafify with respect to this topology. It's a technical construction, doesn't really matter. You can do this, and it forms kind of a derived category of spectra. And again, we can also do an internal construction. So this is this is like for the whole category of spectra, and we also have an internal version using only the EN local ones. And I'm running out of space. Okay, we're gonna remove this, and then we're gonna have a remark in the corner. That's always fun. So there's also, if you prefer like filtered spectra or spectrology-based geometry, there's also versions you can make of this. So for example, Rocker-Goric has a version of this deformation picture using spectral stacks. And in particular, you can take like the category of, so okay, X, I guess. Category of quasi-coherent sheaves on the connective cover of the moduli stack of formal groups, and these are like the spectral non-connective moduli stack of oriented formal groups, and then you take its connective cover. And you only take the kind of substack with height in less than n information. And this is again a deformation between SPN and E star E. Has a nice tau map coming from spectrology of geometry, and it deforms in all the correct ways. There's also a version to do this with the filtered spectra. For example, Scholl-Barkan has a model using filtered spectra. So this is by Gregoric. And the last one we'll do is by Scholl-Barkan. And his model is, you take the totalization of modules over the weighted tower of the Amitzer resolution of the ring spectrum E in filtered spectra. And this again also deforms nicely between these guys. Okay, so now we have a really chaotic page I see here, but there's a bunch of different versions of deformations. Let's try to compare them and see how these all relate together. So at the center, I'm gonna put a hypercomplete synthetic spectra, because these are the things are usually compared to, and just because this was kind of the first deformation in some sense. And then I'm gonna put this internal one, and then we have I didn't put hypercomplete earlier, but let's do this now. Hypercomplete perfect derived category of SP, and then we have the internal one, which is just using SPN instead. And we had some more. We had the connected cover of MFG oriented. And we also have the filtered models. Totalization of modules over And I can also put one more. So people interested in, for example, like slice filtrations and things like this will maybe be familiar with the descent filtration, or the MU, the self-descent filtration on the sphere. This is a filtered spectrum, and you can do the same thing with the EN local sphere, because E is descendable, and you get like a model using modules over the descent filtration on E, and this is also a different kind of model. And I've maybe forgotten some things, but it doesn't matter that much. Oh, one more I can add is if you take big category of synthetic spectra, pure synthetic spectra, you can localize at like a synthetic version of E theory. This is also a different model. So now we have a bunch of different things, and we can relate them. So I've already said that these guys are equivalent. In Irakli and Piotr's paper that I mentioned before, they prove that these guys are equivalent. And in Piotr's original paper on synthetic spectra, he proves that these guys are equivalent. You can also prove the same proof that that works for this guy, works also for this guy. So you can prove that these are equivalent. Rocker-Gorick proves that these are equivalent. And Stolberg-Kahn, he mentions that these are equivalent without proof, but he's a smart guy, so I will believe him. And this last guy, you can use some machinery set up by Berkeley and Hans Senger on some general deformation machinery for stable infinity categories. And these are equivalent under a certain asterisk. So the asterisk is if this cellular, so it's generated under filtered co-limits by the EN local spheres. Yeah, okay. This is a technical condition, but it's something that at least I expect to be true. And I haven't been able to prove it yet, but hopefully in the future there will be a proof. There are a bunch of different categories where this works. So if we take inspiration from this, then not only Syn E is cellular, but the category of MU based synthetic spectra are cellular, the category of FP synthetic spectra are cellular, and in particular, if you have any connective ring spectrum R, then Syn R is cellular. This is a recent proof by Taylor-Lawson. So since MU and also, I guess, also BP, for those who know that what these guys are, since these guys are kind of very related to this guy, I also highly expect that this guy will be cellular. But the proof escapes me so far. Okay, so the general picture is that all of these relate to each other, at least up to the last one, and we know kind of the structure of where everything is equivalent. So in the last section here, I want to just discuss some chromatic analogs of these guys, and they will all have two different ways of generating them. So if I have some deformation D that deforms between SPN and the E star E, then I'm gonna use my fancy local duality machinery that we mentioned before. So I have some monochromatic category, and I have my KN local category. And I'm gonna try to do the same thing here. Here I have some, I really didn't give myself much space, but these are like some sort of complete derived category. And this is some sort of torsion derived category. So I want to use the same thing and kind of set up some monochromatic versions of this guy and some KN local versions of this guy. That's kind of the goal. Okay, so there's a bunch of different ways you can, again, do this, because a bunch of the different constructions for E-theory come with maps from spectra to this deformation. So I have my SPN guy, and in here there's a EN local finite type N spectrum that generates this subcategory MN. So now I'll write this at this mirror. Okay. Yeah, let's write it like this. Okay.
So there's a question in the chat. So isn't it simpler to compare mod fill with LE synthetic E? I guess it's easier to see that EN local spheres are generators for sheaves over finite projective spectra. To place that in.
Yeah,
Just
I've been thinking about that as well. I think it's more, as you say, it's more directly comparable to the internal model of synthetic spectra, and I have also some like hopes for this being more directly comparable to Scholl-Barkhan's model, and also yeah. Okay, I can also say that in Rucker-Gorg's paper, he mentioned that these two are equivalent, but I don't believe that his proof works for non-cellular stuff, because he uses the Birkeland-Hahn-Sanger machinery, which I'm fairly certain means that this guy would have to be cellular, and it might be that it is. Or no, wait, the synthetic guy, yeah. So. But yeah, there's a bunch of different ways to compare these, since there's a bunch of different related constructions and factors. But yeah, probably some of them are easier than others, I agree. Okay, yes, this monochromatic category is constructed as the localizing ideal in SPN generated by FN. So if I take my version of monochromatic synthetic spectra to be the localizing ideal in hypercomplete synthetic spectra, tensor ideal generated by the synthetic analog of VFN, then I do in fact get a deformation diagram of the form MN soon, E, and on this side, it's a nice derived category of a certain subcategory of all E star E comodules, which are torsion with respect to some naturally occurring ideal in pi0 of E. Okay, so there are ways to do this. That's the kind of the cool thing. Okay, we can try to also do this dually by instead of we can take the oh wait, not dually, internally, I mean. So instead of taking the localizing ideal, we can do an internal construction as we did earlier, and instead look at kind of sheaves of spectra, which are spherical, on some site of monochromatic finite projectives. This is more complicated because torsion and projective is rarely unifiable in some sense. Things that are torsion are usually not projective. But I think there's a way to, I think there should be like enough projective stuff to make this happen anyway, hopefully. But yeah, this is another attempt you can do. And you can also make, of course, monochromatic versions of some other constructions. So for example, if I take the perfect derived category still with respect to the same homology theory, but now I restrict it to this monochromatic category, then a paper I put on the archive last week showed that this also works, or it implies it works. It's not actually in the paper, but what you need for this thing to work is that you have an adaptive homology theory, and you can prove that E star on Mn is adaptive. So this guy also deforms in the correct guy. Okay. What about some direct approaches using Kn? So I said that if we have this synthetic analog of Fn, then I can also do localization on the spectrum. So if I do localizing on this, on hypercomplete synthetic heat-based spectra, this I can call like Kn local synthetic spectra. And you can also prove that these guys actually have the correct type of deformation picture. So we have L, K, and sin. And now a technical condition is that this completion thing is on the outside of the derived category, whereas before it was on the inside. This is, it looks innocent, but it's incredibly annoying. Because if you try to like take the category of comodules over E star E, which are complete, then this is not an abelian category. So kind of then all the naive things you can try to do with constructing Kn local deformation theory would have to use kind of versions of this guy, and it straight up just doesn't work because it's not abelian. In particular, the natural thing that we should call like Kn local E homology theory is not really a homology theory. Yeah, and the other approaches also like taking Morava modules and stuff like this is the same thing, but it's also not the homology theory, unfortunately. But this thing works, like localizing at the synthetic analog of at En local type N spectrum actually deforms the correct way. There's also, you can do these spectral algebraic geometry analogs, and I don't have time to tell you much about them, but I'm gonna show you a picture about all the different variations of these different Kn local or monochromatic modules that we have, and I'm gonna try to relate how this weird network of deformations are related. So these are the different ones that we have been discussing today. So these are the perfect derived categories, and you can also make local duality theories with these guys. And here should be the Kn local one, but as I just told you, since we don't have an abelian model, this one doesn't work. So that's why it's missing. And then we have all the synthetic models. So this is monochromatic synthetic spectra that we constructed. And this is the Kn local synthetic spectra that we just constructed. And you can also make like local duality theories. And yeah, these are again like the spectral algebraic geometry versions. And you have some filtered models at the end. Okay, so how does these all relate to each other? So first of all, a bunch of them relate via just local duality. So you can, now this yellow means that these are equivalent using local duality. Okay, and then we have a bunch of more hypothetical things. So in some sort of way, as I just mentioned, you have an equivalence between E star E torus and the E star E torus. So I can kind of pull the torsion inside. And I said that you can't do this for completion, but all of these guys, which I'm now painting in with blue, is kind of an analog of this phenomena happening. So it's about like pulling torsion information inside of the derived construction in some way. So you can some of these I have proved. Some of them are conjectural. But yeah, most of them I feel like they should go through. Okay, so now we have kind of these layers of equivalent stuff, and some of them are also equivalent because we know that without the torsion, for example, these guys are equivalent. So once we take the torsion, they're also equivalent. The same thing with these guys, and yeah, I'm gonna say these guys because Schall tells us that they are, and I'm inclined to believe him. And yeah, this guy is still like if cellular, so I'm not gonna write that in. But this also works for these guys. So okay, now we're left with like a little group on the right here, and we can also prove that these guys are equivalent. That was basically the definition we used. And it remains to be seen how these three relate to the other ones. I have so far no idea. I hope to figure it out. Somehow this should like use that Kn is also like gives descendable information, which is like a difficult result proved by Akel Matthew. And doing filtered things in KN local spectra is also more complicated because you change the tensor product and you don't have the same one that you have for spectra. You need like a completed tensor product. So things along these lines, which uses a bunch of the tensor structure, is very complicated. Okay, so this is the mess of KN local deformation theory and all these, how many, 24 different models should hopefully be all equivalent, but it remains to be seen if that's actually true. So yeah, thanks.
Thank you. Yeah.